Okay, hello. Today we're going to solve some trigonometric inequalities, and these start off kind of easy and maybe are even sort of common sense and quickly get a little bit more challenging. Okay, let's begin. Sort of the most simple basic thing would be if you were presented with an inequality like sine x. Sine x is greater than 0. Okay, so when is sine greater than 0? This seems like a pretty simple thing to answer. Sine is a trig function which is defined to be the y-coordinate of a point on the unit circle. I think the way to do this problem, the best way, is to think geometrically about what's going on. So I will just draw a picture of a unit circle, and when is sine positive? I think the answer is pretty clear. Sine, like I said, is the y-coordinate, so sine is going to be positive kind of everywhere here. So in some ways we're done, and I don't want to lose sight of kind of what's important. I think this is what's important. What's important is we've answered this question by shading a region of the unit circle, which is ultimately where the real thinking happens. Okay, of course we still want to give an answer, and the answer is everything from 0 to pi. And so if this problem had a kind of an implicit restriction, so supposing someone said, hey, on the interval from 0 to 2 pi, this is the kind of thing that people say sometimes, then for all these numbers, in other words, for just one kind of revolution or something of the unit circle, when is sine positive, the answer would be just from 0 to pi. So that's kind of an answer, but if that was not a restriction that was given, and instead someone was asking just sort of more generally, give me all real numbers for which sine is positive, then 0 to pi is not wrong, however it's not the complete answer, because of course if I go all the way around the circle again, then this is 2 pi, and so all the numbers between 2 pi and 3 pi also have a positive sign. And of course, pattern is just going to hold, right? So the real answer to this problem is something like everything from 0 to pi and everything from 2 pi to 3 pi. Those are perfectly legitimate real numbers after all. And it's just a fact that if you take the sign of 2.5 pi or something, you're going to get something positive. So this certainly deserves to be mentioned. And this is going to kind of go on forever and forever backwards as well. And so the answer to this problem, stated as a set of real numbers, is going to be an infinite number of real numbers composed of the union of sort of an infinite number of intervals. And so the way to think about this is sine will be positive for any number which is sort of between some even integer multiple of pi and pi more than that. Alright, so if you said k equal to 0, you get our first answer. If you said k equal to 1, you get our second answer, etc. Okay, this is good enough to satisfy virtually everybody, this kind of statement. And it's already maybe overkill, but to take it kind of one more step up into overkill, I'd like to give a slightly better answer, because of course this is just kind of a statement about x values. I would like to give a set, because the answer should be to an inequality. It should be the set of real numbers which satisfy the inequality. And so we should really have some kind of notation for the union of an infinite number of intervals, and we do. We can say it's the union of a bunch of intervals, each of which is of the form 2k pi to pi plus 2k pi. And we union among all the integers, so this is like the index of the union. Alright, so this is a little bit of a maybe overly fancy kind of a final answer, but there it is. This is maybe the best way of answering this problem. Okay, good. Let's do some more. I did this for my own students. I did that problem in class, so there was nothing. This is not helping them. Here's another one that I did in class. When is cosine x less than or equal to 0? Okay, well, the exact same logic applies. We can just do this, I think, more quickly now that we got the gist. We draw a unit circle. we invoke the definition of cosine, which is that cosine is the x-coordinate, the horizontal component, or something. And so, for what angles is the cosine negative? Well, cosine is going to be negative in quadrant 2 and quadrant 8. So we shade all the parts of the unit circle, and like I said, you're really substantially done with the problem at this point. Everything beyond this point is just kind of being very precise and particular. This is pi over 2, and this is 3 pi over 2, and the answer to this problem is just going to be everything from pi over 2 to 3 pi over 2. But of course that's not the full story, because I can go around the whole circle again, and the period of cosine is 2 pi, so in fact this is going to just repeat every 2 pi. So, if it helps you, you can sort of write this intermediate answer, which is that a solution to this inequality is going to be everything from pi over 2 plus 2k pi to 3 pi over 2 plus 2k pi. And now I want to use less than or equal to, of course, because the points themselves, actually this picture is a little bit wrong, because I do want to include those endpoints. Okay, good. And finally, I can write this as the union of an infinite number of intervals, each of which now is a closed interval of the form pi over 2 plus 2k pi to 3 pi over 2 plus 2k pi. Okay, good. Going a little faster, 16 is not a problem that I did with my own students. So for my students who are watching this, okay, it's maybe not that hard. When is tan positive? Alright, so it's a little bit more difficult to envision tan on the unit circle, but not much, because I know things about the tan function. It's the ratio between the y-coordinate and the x-coordinate for a point on the unit circle. So tan will be positive when either x and y are both positive, so quadrant 1, or both negative, so that's quadrant 3. And okay, so that's all there is to it. These are just some basic facts about the tan function that we're also kind of reviewing. Okay, so yeah, so you might think, okay, how am I going to write this now? This is kind of annoying. Everything from 0 to pi over 2, and also everything from pi to 3 pi over 2. And there's some kind of symmetry here, and in fact, that symmetry is not a coincidence, because the tan function just has a period of pi. And since the tan function has a period of pi, then it suffices to consider the behavior of the tan function on only kind of like one half of the unit circle, because well, after that it's just going to repeat. Okay, it's just a way of saying, hey, if this function is repeating every pi, then I can merely analyze the function on one of its intervals, a period length interval, and then just sort of repeat. Okay, so this is a long-winded way of saying that when is tan going to be positive? Anything between 0 and pi over 2 plus k pi. And when k is 0, you get the answer from 0 to pi over 2. When k is 1, you get the answer from pi to 3 pi over 2, and then it's just going to keep repeating every pi. So actually this is sort of the fastest or something, or most efficient way to answer this problem, is to just say this. Okay, so that was just maybe a little trick or something, or kind of a reminder that that the period of the function is relevant. More. 17. This is also one that I did in class. 2 sine x is greater than or equal to 1. Okay, what do we do now? Well, we just do it, right? If 2 sine x is greater than or equal to 1, that means sine x is greater than or equal to half. So again, I will draw a picture because I'm thinking about this whole thing geometrically. When is sine 1/2? These are just facts that I know because I just know the unit circle. And the answer is it's going to happen from pi over 6 to 5 pi over 6. So when is the height of the point going to be positive? Exactly right there. Alright, so I'll just go kind of maybe right to the answer now. It's going to be everything of the form pi over 6 plus 2k pi to 5 pi over 6 plus 2k pi. And these are greater than or equal to, so again I will use brackets, so I should think of this as a union of an infinite number of closed intervals, each of which is of this form. Okay, one more, and sort of for my own students, this is one that we didn't do in class, but it's maybe also not so hard. I might encourage you to start watching the video sort of now, so you can see everything we've done. What's the solution to this? Well, it's going to be when cosine x is greater than a half. And for that, I just make a picture. So when is cosine greater than a half? Well, when is cosine equal to a half? Cosine is the horizontal component, so that's going to happen here and here, and kind of like everything in between. So what is that? That's pi over 3. And okay, you might think of that as 5 pi over 3, and that's not wrong, but if I want to refer to this sort of interval, then it doesn't make any sense to go to say from 5 pi over 3 to pi over 3. That would just be wrong, because 5 pi over 3 is like a bigger number, right? So I'll say that it's everything from negative pi over 3 to pi over 3, and that is in fact going to just repeat every 2 pi. So the answer here is the union of a bunch of open intervals, each of which is of the form negative pi over 3 plus 2k pi to pi over 3 plus 2k pi. Okay, good. So I would call all of these so far sort of easy and straightforward. There's not much of a technique except for just being careful and knowing the definitions of your trig functions, knowing your special angles, writing it out, and taking the kind of time and effort to sort of draw the little picture and shade the region on the circle. Okay, but you probably would have gotten all these answers right, maybe without even any direct instruction. Then they do start to get, a little bit harder. So okay, I'm going to erase all this, and we're just going to do the rest of this page. Starting to get some water here. Okay, good. So we pick up where we left off. 19 says tan x is greater than or equal to 1. Okay, I'll do this kind of fast because I did do this in my class. And this was sort of the last thing we were doing at the very end on Thursday and Friday. When is tan x greater than or equal to 1? Well, we said that tan x equals 1 at pi over 4. And then I kind of remarked, at least to some classes, that tan, you should think of tan as the ratio between the x and y coordinates. And so when you have points on the unit circle where the ratio between the height and the width is much greater than 1, then that's when you have a large tan. And so it starts here at 1, and tan gets increasingly bigger over the interval from pi over 4 to pi over 2. Now you might be thinking about the graph of tan, and that's of course a whole nother approach to doing this problem is simply to have memorized the graph of tan. But it's really the definition of tan based on the unit circle which tells you about the graph. Actually the sort of reason why we know that the graph looks the way it does is because of this kind of geometric analysis. Anyway, I'll stop there because tan is negative on quadrant 2, so of course that is not going to be a solution because we're looking for when tan is greater than 1. And as I mentioned a few minutes ago in the video, now the sort of smartest way to proceed from here is to observe that the period of tan is pi. And if the period of tan is pi, then I need only look at tan on the interval from 0 to pi and then just say that it repeats, which it does. So the answer is going to be something like, well, any time x is between pi over 4 plus k pi and pi over 2 plus k pi. Here tan is undefined at pi over 2, but if x is equal to pi over 4, I want to count that as a solution because it's greater than or equal to. And therefore the answer to this problem, as I said in class, is the so-called half-open interval, so closed on the left and open on the right, from pi over 4 to pi over 2, but then sort of repeated every pi, so an infinite number of those. Okay, that's where we ended, and I think sort of all of a sudden, you know, things get hard, starting kind of now. So my students are definitely going to watch this video from this point on, because they may very well get all of these right, but I think it's difficult to get all of these right. So let's go, and there's sort of good ideas and bad ideas maybe here. So okay, number 20. Tan squared x is greater than 3. Alright, this is, you know, pretty hard, and so what should we do? Well, it's important when doing problems like this to kind of already, like, you know some things. So there are some things which come up so often, such as quadratic inequalities like this, that maybe it's worth it to just kind of have a good sense of them. So I guess I am hoping that everyone in my class, and maybe everyone watching, just already knows how to just like intuitively feel their way to the right answer for some sort of simple problem like, when is x squared greater than 16? Okay, so here you would think, okay, well, if x, common sense says, numbers bigger than 4, right? When you square a number bigger than 4, then it's going, well, any number bigger than 4 when squared will be greater than 16. But that's of course not the whole story, because we have to also keep negative numbers in mind. And so can the square of a negative number be greater than 16? Sure, because say negative 5 when squared will be also greater than 16. So the answer here is going to be if x is less than negative 4, or if x is greater than 4. So, I don't know, to me this is sort of simple enough that you just think about it and then there's your answer, and there it is. There are other approaches here, of course. So what would the answer to this problem, if someone gave you this inequality and told you to solve it, this might be hard for an Algebra 1 student or something, but what would the answer be? Well, it would be everything from negative infinity to negative 4, union everything from 4 to infinity. So that's the right answer. Are there other ways to do this? Sure there are. There's the way in which you just think of the graph. And so maybe you have some kind of parabola in mind, and you ask yourself, you know, when is it bigger than 16? And the answer is going to be, you know, over here when x is bigger than 4, and over here when x is less than negative 4. That's one solution. There's even the potential idea that you might bring x squared, bring the 16 over to the other side. This is, after all, what I taught you. And, you know, factor or something like that. So, you know, x minus 4, this is also sort of a possibility, right? Is positive, and when is that true, you can make a whole sort of sign chart, and you can see that this is negative 4, this is 4, this is kind of a quadratic, so it's going to be positive, negative, positive, and you can sort of see. So, whether you want to do that all out, or whether you want to just kind of think about it for a second and sort of just know the answer, or whether you want to think of the graph, you know, one way or another you should become comfortable enough that this doesn't take a lot of effort. So, okay, assuming we've just sort of mastered that kind of a thing, then I would say that this is sort of that category, right? When is 10 squared going to be bigger than 3? Well, the square of something is going to be bigger than 3 when that thing is either bigger than the square root of that number or less than the negative square root of that number. In other words, I'm hoping that everyone sort of sees that the next step to sort of decompose this is to say it's whenever tan is bigger than root 3, or when tan is less than negative root 3. And that's basically it. One way or another, you have to have the ability to get from here to here. And once you hear that answer, of course that's right. Yeah. If the tan of something is bigger than root 3 and you square it, then it will be bigger than 3. And conversely, if you give me an x such that the tan is less than negative root 3, then when you square it, it'll be also the magnitude will be bigger than 3. Okay, so all right, it's taking too long. Now I really just have two separate problems to solve. When is tan bigger than root 3, and when is tan less than negative root 3? Well, I can make a picture of this, and let's sort of do it. Well, when is tan root 3, first of all? That is something that you should just know. And, well, okay, stick to my convention of using red for my shading. It is up here. Up here at pi over 3, tan of pi over 3 is root 3 over 2 over 1/2, so that's root 3. And as we kind of discussed, the picture's right here. As x gets closer and closer to pi over 2, the tan gets larger and larger. And so the answer to this problem is sort of all of this. It's everything from pi over 3 to pi over 2. So that's the solution to these kinds of problems. When is tan less than negative root 3? So when is it a large negative number? Well, alright, maybe you have some good intuition on this, maybe you don't, maybe you're going to get it right now, but it's going to be all this, right? Because, of course, tan is negative in the second quadrant, but when is tan a large negative? Tan is a large negative when, once again, the ratio when the y coordinate is much bigger than the x coordinate. So by symmetry, both of the points kind of near pi over 2 have very large y coordinates relative to their x coordinates. This is the kind of geometric way of thinking about it. So here tan will be a large positive, and here it will be a large negative, so it's 2 pi over 3. Okay, so that's basically it. And now I'm not even going to bother drawing the bottom half of the circle because I feel like it's just a waste of time and effort because this function is periodic, tan is. And so as long as I answer it for one little interval, then I'd be done. So, how should I do this? Now this kind of gets a little bit annoying, right? Because there's no really good way to write this. So I'll say, all right, well, what is it? It's really like two intervals, right? It's everything from pi over 3 to plus k pi to pi over 2 plus k pi, but then sort of excluding pi over 2, right? So then from pi over 2 to 2 pi over 3 plus k pi, and I throw a bracket in there, and now, okay, technically speaking, I should probably even have some sort of extra, grouping symbol or something like that, around this whole thing to indicate that I am, I'm taking the union of sort of everything of this form. Okay, but really, this is the important part, right? It's all that stuff. That's the important math part of this. Okay, let's keep going. The next two are also tricky. 21, 22. Let's go. 21. What's 21? 3 secant squared x is greater than 4. Oh man, this is so hard. What am I gonna do? Well, maybe first I would just do some stuff. So, alright, well I'll get secant squared x is greater than 4/3. At least I can do that. That got a little bit better. And what's kind of very annoying here is that I don't like secant. It's confusing, it's weird, I can't draw it on the unit circle. It's undefined in certain annoying places and stuff like that. So, well, let's just fix that whole problem, right? Let's just fix that whole problem by converting secant into cosine. So what is secant? Secant is just really it's just 1 over, secant squared is 1 over cosine squared. So that's just because secant just is 1 over cosine. That's just almost the definition of secant. It's the x-coordinate. It's 1 over the x-coordinate. Well, there it is. This is great because now it means I can express everything in terms of cosine. Well, I would like to simplify this a little bit, and here we use the thing that we did in class just the other day, which is to observe that the fastest way to proceed here, as long as everything is positive, which it is to just reciprocate both sides and flip the sign. So if 1 over cosine squared is greater than 4/3, then cosine squared is going to be less than 3/4. And now I've got it down to basically a very kind of manageable and pretty easy problem. When is cosine squared less than 3/4? And the answer is, well, just like before, this is now the kind of reverse of the problems that we were just doing over here. Maybe I'll kind of do this or something. Maybe it's even easier somehow to see when is x squared going to be less than 16. This is another sort of just basic kind of principle of reasoning with quadratic inequalities. Well, if x is small, then when you square it, it's going to be less than 16. How small does x have to be? Less than 4. So if x is less than 4, but also negative numbers are legit as long as they're not too big. And so in fact, the solution, I think that's pretty just immediate, is that x squared would be less than 16 for any x between -4 and 4. Okay, so if you have this kind of thing in your brain, then when is cosine squared going to be less than 3/4? Well, that will be true whenever cosine is between √3/2 and -√3/2. I sort of said that backwards, but it's like this. So for any x's such that the cosine is pretty small, in this case small f is √3/2, then when you square those numbers, they'll be less than 3/4. Okay, I think that's pretty clear. So everything now has just gotten down to this point. So can I solve this inequality? Yeah, I can. I'll do it by drawing a unit circle and shading appropriately. So cosine is the x-coordinate. When is the cosine going to be between -√3/2 and √3/2? Well, actually, most of the time, right? When is cosine √3/2? Over here at pi/6, and here, and here. And so I want to know all the times that the cosine, the x-coordinate, is sort of between those. So I want almost everything. I only want to exclude when cosine is bigger than √3/2 is one way of putting it, or something like that. So this is the answer. Once again, once you've done this shading, I consider you to have be 85% correct or something like that already. But if you want to write out your final answer in some kind of coherent manner, then you can do that as well. And I think now, because of the symmetry repeating every pi, I think we can just say it's going to be the union of all of the intervals of the form pi/6 plus k pi to 5 pi/6 plus k pi. And then knowing that this is just going to repeat from there. Okay. Good? Good. Okay, 2 more to go on this page. Maybe 1 is easy. Kind of 1 is hard. The last one. Okay, I guess I'll just erase everything. Okay. Oh yeah, let's just do it. 22. 22 says this is 2 sine squared x is less than or equal to 1. Alright, so immediately I'll rewrite this as sine squared is less than or equal to 1/2. Well, actually, this just turned out to be almost exactly like the previous problem. Because if something squared is less than 1/2, then it means that that thing is not so big, and in this case, not so big means between √2/2 and √2/2 and -√2/2. because that's just the square root of 1/2. The square root of 1/2 is 1 over root 2. You could also just write this as 1 over root 2. That's the same thing. Okay, so what? Well, I draw my unit circle, and I say, when is sine between negative root 2 over 2 and root 2 over 2? Alright, when is sine equal to those numbers? That's at like pi over 4, and blah, 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 blah. So the sine is the y coordinate, so when is the y coordinate kind of in between those two, so you know, sort of temperate zones or whatever. And so here, maybe what I would do is just say, okay, well that is negative pi over 4, that's pi over 4, so it's going to be all those, and then that's just going to repeat every pi. So once again, I just observe the symmetry, and so perhaps it's faster to just say everything of the form negative 4 plus k pi, and here I use brackets, to pi over 4 plus k pi, and I will take the union of all of those. Okay, good. The last one has a little bit of a twist to it. So this is 2 cosine 2x, and is less than root 3. So what should we do? Okay, well, the first thing I can do is just rewrite this as cosine 2x is less than root 3 over 2. And I guess the best way to do this, so this is what makes this kind of tricky is because there's sort of something else in here. So when you see this, you might sort of not know what to do or kind of panic or something like that. Well. Okay. So maybe I'll just tell you what to do, and then we'll talk about how you could have gotten that kind of wrong. What's probably the best method? The best method, I think, is to still do it visually on the unit circle. And so basically, what I want to do now is just kind of think of this 2x as like a single variable for a minute. I don't know, call it whatever you want. Call it y, call it theta. Don't change the name at all, but just think of it as a unit for the moment. So let's just solve the problem. When is cosine less than root 3 over 2? And then we'll sort of deal with the 2x part kind of later. All right. So by that I mean draw our picture. When is the cosine root 3 over 2? Well, that's when the cosine is quite big. So that's going to be over here at pi over 6 and at negative pi over 6. And when is cosine therefore going to be less than root 3 over 2? Well, sort of almost always, right? So I shade virtually the entire unit circle. And okay, so here, if I want to talk about these, I should probably go say from, all right, so from pi over 6 all the way to 11 pi over 6. Okay, and sort of noting that this is kind of like theta that I'm talking about here. If it makes you feel better to use this temporary variable, then you can. And so ultimately, if you want this kind of crutch, then basically what we're really doing is we're kind of we're solving the inequality when is cosine theta less than 3/2, and then we'll sort of later substitute back in the fact that it's really 2x. I think this is the way to go. So all right, when is cosine theta less than root 3 over 2? Answer: it's going to be not just from pi over 6 to 11 pi over 6, but also an infinite number of other sort of times, which is why we've gotten pretty good now at being kind of abstract and general like this, and saying that it's going to be everything from pi over 6 plus 2k pi to 11 pi over 6 plus 2k pi. Okay, but while that's definitely true, this theta was just kind of a temporary creation of mine. Really, theta was just a shorthand for 2x. And so, since cosine is less than root 3 over 2 between these two numbers, then my goal is to find out for what values of x this is true. And so, okay, I gotta just sort of take my final step, which is to divide by 2. But having taken the care to write it out sort of generally like this, then everything sort of works out, because now my answer is that it's when x is between pi over 12 plus k pi and 11 pi over 12 plus k pi. Okay, and so that's it. And there's kind of the answer. The answer is going to be, it's everything from pi over 12 plus k pi to 11 pi over 12 plus k pi. But this is an example where, had you been a little bit less careful, you could easily get this problem kind of wrong. I guess because if you just took the interval, well, let's just now sort of retranslate. Let's retranslate the answer right here, which is correct, back onto the unit circle. So let me just shade now. This time I'll maybe shade in blue just to stress. Well, okay. So what is pi over 12? It's going to be like over here, and 11 pi over 12 is going to be like over here. And so yes, everything from pi over 12 to 11 pi over 12 is an answer, but so is everything from, and if you plug in k equals 1 here, you see that everything from sort of 13 pi over 12 to 23, I guess it is, right? Pi over 12 is also an answer. And I might have kind of missed that because, let's see, how to explain this exactly. I guess the period of cosine 2x is pi. And so, since the period of cosine 2x is pi, when I'm only kind of halfway around the circle, I'm sort of not done yet, right? There's a whole other half of the circle left to go. And so this is the sort of full kind of representation of the answers. Well, this picture didn't capture the fact. Let's see, it's difficult to articulate exactly what I'm trying to say here. But anyway, this is definitely the right answer. And I think that the simplest way to deal with these sort of changing arguments is to just do the picture analysis and then kind of use algebra to modify afterwards. Okay, because you might have missed. I guess what I'm trying to say is you might have missed this this second bit here because it is true that for x values between 13 pi over 12 and 23 pi over 12. That when you multiply them by 2, what happens? Well, you end up at 13 pi over 6, and it is true that sort of from 13 pi over 6 to 23 pi over 6, that the cosine is less than root 3 over 2. But you might have sort of forgotten about that or something. So, okay, I'll leave it at that. Let's see, how long is this video? It's already sort of long. I guess I'll just push on. I'm going to take a break for a second and be right back. Okay, back for the last two problems. These last two problems are quite hard. So this is really, I'm really sorry, Precalc C, but Zoom school, we have to learn this via video. But this is actually like a very important topic. Well, very important. I mean, you know, in the big scheme of things, whatever. But I think this is an important skill. So I would definitely, in a normal year, have taken real class time on this. So you really have to watch this video. Here it is. What should I do when presented with some kind of crazy, complicated inequality like this? And this comes up a lot. It comes up in calculus where we have to solve kind of difficult trigonometric inequalities like this. So this is really like a new skill, but also kind of a follow-up to the previous page. All right, so what should we do? Well, to bring some kind of sense to this, I should probably try to factor. And well, what do you know? It really does factor. 4 terms, so factoring by grouping is a possibility, and in fact, it's a good possibility. So if I factor out 2 sine x from this, then I get 2 cosine x minus 1 plus, and here I just have again 2 cosine x minus 1 is greater than or equal to 0. And so maybe if you want to do this or something, that means that I can now factor. I have basically 2 terms. I can factor 2 cosine x minus 1 out of both of them, and this will be 2 sine x plus 1. Okay, so great. Now what kind of? Well, now if you're getting really good at solving inequalities, and we are, then we see that we really just have a product of 2 things. And so we want to know, when is that product positive? Well, that product will be positive when these are both positive or when they're both negative. So the bottom line is I just need to know for sort of all real numbers when each of these factors is going to be positive and when it's going to be negative. So let's just do that right now. So let's determine when so I'll even just write it. So side project, when is 2 cosine x minus 1 going to be positive? And over here, I'll ask the question, when is 2 sine x plus 1 going to be positive? And now I'm just going to solve these 2 things separately. Okay, well, let's do that. I know how to do this. So this is going to be, when 2 cosine x is greater than 1. So that's when cosine x is greater than half. Okay, so make my little picture for this. And what is the picture of all the times that cosine x is greater than a half? Well, cosine x is a half. Up here it's pi over 3. And so it's going to be all of this. Yeah, that's that. And what are these numbers? Maybe I want to call them everything from kind of negative pi over 3 to pi over 3. Those are going to be the numbers where the cosine is greater than half. Looks good. It is good. Next, when is 2 sine x plus 1 going to be positive? Well, I know how to do this also. That's when 2 sine x is greater than negative 1. So that'll be when sine x is greater than negative half. And, well, when is that true? Well, I make another kind of little picture here. And so we say, well, when is sine equal to negative a half? Answer kind of down here at negative pi over 6. And the other time that sine is negative half is at 7 pi over 6. So basically all of this. Yeah. Cha. Okay, and great. So I'll even just kind of write this. That's negative pi over 6, and that's 7 pi over 6. Okay, well, I've kind of answered now my 2 individual questions, which is when each of these is positive and negative. Now I kind of want like a comparison between the 2 of them, because what matters now is whether I really need all the times that they're both positive and all the times that they're both negative. Okay, so here comes this kind of a brilliant move. You could take these circles and kind of then convert them into number lines or something and compare the number lines, but no, the much better way to do this, I think, is to just make a big circle. So this is this method that this kid came up with a long time ago, which is just really kind of beautiful and elegant, and that is sort of overlapping circles. In other words, I'll draw on one of the circles, kind of going a little too slow here. On one, I'll draw, this answer, the one I already had, and then I'll sort of, in another layer or whatever, maybe I'll use purple now, I'll do the other answer. And so now these kind of concentric shaded circles serve to indicate kind of visually with a direct comparison when things are positive and when they're negative. And so, well, maybe I'll just kind of go from 0 to 2 pi. Maybe that's the simplest thing to do right now. First, just as a kind of a warm-up or something. So what's that? So that's pi over 3. That's 7. That's 7 pi over 6. That's 5 pi over 3, and that's 11 pi over 6. And so, suppose you just wanted to do this on the interval from 0 to 2 pi. Let's just take that as a task that we want. And well, okay. Well, let's just look at our shaded sort of double circle overlapping pattern thingy, and just say, okay, well, from 0 to pi over 3, they're both shaded. When did I shade? Well, I shaded, recall, I shaded the sort of the solution to when is cosine x greater than a half, which was also the solution to when 2 cosine x minus 1 was positive. In other words, I decided kind of arbitrarily as a matter of convention that I just established, hey, let's shade when the thing is positive. So shading indicates that this factor is positive for that input. And this shade over here, which got converted into purple, this shade indicates that this factor is positive. And so basically when they're both shaded, which happens on the interval from 0 to pi over 3, that's my visual indication that for all numbers between 0 and pi over 3, they're both shaded, which is another way of saying that these are both positive. Well, if these are both positive, then their product is positive. How about between pi over 3 and 7 pi over 6? Well, here I'll just throw in 7 pi over 6 on my number line. And okay, well, yeah, in between pi over 3 and 7 pi over 6, we can see kind of at a glance that the inner circle red arc is unshaded. And by default, I do not shade when 2 cosine x minus 1 is negative. And I do shade the purple when 2 sine x plus 1 is positive. Okay, so what I'm just trying to say is on this interval from pi over 3 to 7 pi over 6, since one of them is shaded and one of them isn't, that means one of the factors is positive and one of them is negative. And therefore their product is negative. From 7 pi over 6 to 5 pi over 3, so here's 5 pi over 3, now they are both unshaded. Well, by default, unshading means negative, because I shaded when the factors were positive. So therefore, since both are unshaded on this interval, that means that both of these are negative. If both of these are negative, their product is positive again. And from 5 pi over 3 to 11 pi over 6, this one is positive, but the purple is unshaded, which means that 2 cosine x minus 1 is positive, but 2 sine x plus 1 is negative, so the product is negative. And then on this little tiny interval from 11 pi over 6 to 2 pi, they're both shaded, so they're both positive, so their product is positive. Okay, so if this problem were asking, hey, give me all the answers, on the interval 0 to 2 pi, which is the thing that happens actually kind of often. They only care about the solutions on some specific interval. Then our answer would be, it's also greater than or equal to 0, right? So that our answer would be everything from 0 to pi over 3, and everything from 7 pi over 6 to 5 pi over 3. 7 pi over 6 to 5 pi over 3, and everything from 11 pi over 6, 11 pi over 6 to 2 pi. Cha. Okay, if we want the sort of full answer in total kind of generality, then I might say the following. I might sort of do like this. Call this negative pi over 6. And then I would probably start there. And I would say, all right, what is the real answer to this problem? It's everything from negative pi over 6 plus 2k pi, inclusive, because it's greater than or equal to, all the way to pi over 3 plus 2k pi, cha-cha-cha. And here they're both, one's positive, one's negative, so the other kind of interval is from 7 pi over 6 plus 2k pi to 5 pi over 3 plus 2k pi. I won't make any more sort of comments about that or anything, but that would be the answer if they just asked for sort of all real numbers for which this is true. Is that what I wrote in my answer key? It is. Okay, so that's pretty hard. The sort of big takeaway is that you should just trust your understanding of inequalities. That when you want to know when the product of two things is positive, then you just need to analyze the two things individually. And with this kind of a system of concentric circles, it makes it very visually clear how to go around the circle in order and see what's shaded and what's unshaded. Okay, good. That was like a whole lesson basically. That's sort of a new topic. Then there's kind of one more practice problem. So okay, I mean, the best thing to do would be if you did this problem all by yourself and sort of struggled in sort of pain and suffering and doubt, and then maybe emerged, with more confidence. But that's something you could certainly do by stopping this video, turning it off, and either never watching it or watching it later. But here I am, I'm just going to do the problem. You don't get as much out of it from just watching me do it, but I don't intend to go over this in class, so this is your chance. 2 sine x cosine squared x minus sine x is the last problem from this packet. When is this negative? Okay, what should we do? The same thing. We should try to... It's kind of a weird problem. So we should maybe try to factor out a sine. So if I factor out sine, then I get 2 cosine squared x minus 1 is negative. And now I need to solve this. Well, I'll stop there. I don't think I want to do any trig identities or anything weird like that. And actually, yeah, I'll just, using the same thought process as the previous problem, when is the product of two things negative? The product of two things will be negative when one is positive and one is negative, but it still boils down to, knowing when each of them is positive and negative. And so I will now kind of do two side projects. When is sine positive, and when is 2 cosine squared x minus 1 positive? Some people, this has bothered some people because it seems like it's negative here, so why am I doing the positive case? It doesn't really matter. I want to know them all, right? I want to know precisely what the sign is, positive or negative, on every interval. But I think if by default we always solve the positive case, well then it just means, I think it's just easier to just think in terms of, hey, when is this positive? When is sine positive? Answer, all of this. So we just shade the positive is I guess my point. And when is this positive? Well, that's a little bit harder. So that's when 2 cosine squared x is bigger than 1. So that's when cosine squared x is bigger than a half. Well, now we're back to, relatively hard problem from the previous page. When is cosine squared x greater than a half? That's going to be when cosine is big, right? Big positive or big negative. And so this is a kind of a follow-up to something we did earlier. One time that cosine squared will be bigger than a half is when cosine is bigger than root 2 over 2. Because when you square that, it's a half. But another time will be when cosine x is less than negative root 2 over 2. Alright, so I won't comment on that further, just think that through until you understand that. And yeah, I mean, this is just a harder version of the basic thing that we talked about already. When is x squared bigger than 16? When x is bigger than 4, or when x is less than negative 4. So this thought process, but now applied in this more complicated context. Okay, anyway, without further ado, let's make a unit circle which we can shade. When is cosine bigger than root 2 over 2? Well, cosine equals root 2 over 2 at all these points. And when is cosine less than negative root 2 over 2 at all these points? Okay, and so I forgot my color coding scheme, but I'm now ready to put it together in one big circle. Of course, you can skip this intermediate step and just go straight to the overlapping. Is probably the thing to do once you're comfortable. So let's do it. When is sine positive? I just kind of copy my work, and in another ring around, I add in this stuff. And when I do that, this provides an easy comparison of when everything is positive and negative. The difference with this problem, well, okay, let's sort of just begin. Maybe it's even nice to label it like, directly on the circle or something. I don't know, maybe people like this. So here, from 0 to pi over 4, they're both shaded, so the product is positive. But from, so all this or something is like positive. And then from pi over 4 to 3 pi over 4, one is shaded and one isn't. So that means one is positive and one's negative, so the product is negative. I don't know, kind of inventing my own system here. But then again, between 3 pi over 4 and pi, they're both shaded again. So since they're both shaded, and by default we shade when the factor is positive, then that means that both factors are positive, so that means their product is positive. From pi to 5 pi over 4, one is shaded and one isn't, so the product is negative because one's positive and one's negative. In between 5 pi over 4 and 7 pi over 4, neither is shaded, which means they're both negative, and that means their product is positive. And finally, from 7 pi over 4 back to 2 pi, one is shaded and one isn't, so the product is negative. And so the actual answer to this problem is going to be, because I want to know when it's negative, the answer is it's going to be everything from pi over 4 plus 2, well, I can actually even be a little bit more kind of cool here or something and observe some sort of symmetry. So let me do that. I'm going to think of this 7 pi over 4 as negative pi over 4. So I'm going to say, alright, everything from negative pi over 4 plus k pi to k pi, that interval, it will be negative. And everything from, am I doing this right? Yeah. And everything from pi over 4 to pi over 2. Okay. In other words, all I'm doing is I'm sort of noticing that this pattern just repeats every pi. And if this pattern repeats every pi, then I'll just sort of give my answer from negative pi over 2 to pi over 2, and then just kind of repeat. Is that what I did on my answer key? I said, on my answer key I said from pi over 4 to 3 pi over 4, and from pi to 5 pi, and from 5 pi to 7, but this seems like good enough, right? Because when k is 0, I get from negative pi over 4 to 0, and from pi over to pi over 2. When k is 1, I get from 3 pi over 4 to pi, so that doesn't work. Wait, what did I do wrong? Yeah, wait, I might be trying to be too fancy. I think this is just wrong. It's kind of doubting myself. Let me just stop trying to be cool. Let me just be lame and just kind of answer the problem in a way that students will find helpful. So, okay, I'll just do the whole thing. When is it negative? We're negative from pi over 4 plus 2k pi to 3 pi over 4 plus 2k pi, fact. And I'm also negative from pi plus 2k pi to 5 pi over 4 plus 2k pi. And I'm negative from 7 pi over 4 plus 2k pi to sort of 2 pi plus 2k pi. Chop. And then you just union up all of these. All right. So I think that's you know, pretty good. All right. Good.